Hello everyone, and thanks for joining this webinar introducing the support of Nvidia GPUs on DPC++. My name is Roman Reyes and I am a technical lead on various SYCL related projects on Codeplay. Together with Stuart Adams, one of our software engineers in the DPC++ CUDA backend project, we will be giving you some more detail on what are the benefits of this new backend and how you can use it in your projects. Codeplay is an 80 people strong company based in Edinburgh, Scotland that designs and implements programming models, compilers and tools for multiple vendors. Our goal is to make AI and HPC open and safe to everyone by contributing to open standards and participating in open source projects. We have presence on multiple standard groups and have partnerships with many different companies in the semiconductor area. In this webinar, we will be introducing the work we have done to extend the DPC++ compiler to support Nvidia hardware. We will start with some introductions in case you are not familiar with DPC++ and SYCL. Then, we will move on quickly to how to use SYCL for CUDA. We will present some details about the design and implementation of the backend, and then how you can use it to interoperate with existing libraries. We'll dig on one step further to explain how to use OneMKL on CUDA as an example of how the oneAPI ecosystem can be used on non-Intel hardware. Let's start with the basics. What is DPC++? Well, DPC++ is a SYCL compiler with a bunch of extensions to target Intel hardware and provide many productivity improvements. Many of those extensions are being proposed to the SYCL standard itself, and we will be including to the upcoming SYCL 2020 standard document, but some others are interspecific, such as some FPGA extensions. The key takeaway is that at the core of DPC++ is C++ and SYCL. If you are already familiar with C++, you can get started rather quickly on DPC++ and SYCL. If you are familiar with SYCL, DPC++ is just adding things on top, so no major change there. Codeplay have been involved in SYCL since the start, and we have contributed many parts of the SYCL specification. Compute CVP, or SYCL 1.2.1 conformal implementation, is a reference implementation for SYCL, and the community edition can be downloaded from our website for free. Compute CVP is part of the Acoran platform, a project that we are starting out from Codeplay to offer an open acceleration platform for multiple HPC and AI frameworks compatible with oneAPI implementations. As part of our engagement with the SYCL and the C++ communities, we have been collaborating with Intel to provide a CUDA backend for the open source DPC++ compiler. This is a novel contribution that has profound implications on the SYCL specification. The work for this backend prompted the SYCL working group to detach the SYCL spec from OpenCL and to present SYCL as a high-level programming model that can target different low-level heterogeneous API, which Stuart will be talking later on. In addition to contributing the CUDA backend, Codeplay will help with the overall upstreaming effort so that SYCL support becomes part of the open source LLVM project, ensuring it is a community-driven project that many can benefit. So what are the advantages of our approach? This backend targets directly the Nvidia CUDA API, not the OpenCL support available on the CUDA platform. So effectively, it converts any SYCL or oneAPI application into a native CUDA application. This is very interesting because for starters, you can now incrementally port your CUDA application to SYCL by migrating your kernels one at a time. But also, if you already have a SYCL or oneAPI application, using this backend, it can now run on any CUDA-based platform without change, although you may want to do some change for performance optimizations. Finally, it is possible to call directly CUDA libraries from SYCL code, so you can leverage the great CUDA ecosystem when you run your SYCL application on Nvidia hardware. This also includes using Nvidia tools, so you can use Nvidia profilers or debuggers for your SYCL application. Let's start with incremental porting. By using the interop task or the newest host task variant that will come soon in DPC++ repo, you can migrate your CUDA runtime API code to SYCL, either manually or using the oneAPI compatibility tool. But you can keep your already optimized CUDA kernels. You can use them to dispatch on your Nvidia GPUs and check that everything else works fine. Your application is still a CUDA application, so you can use any existing CUDA tool you have, like NVProof for example, but you can also use any DPC tool for tracing and performance analysis on the host part. If you use the oneAPI compatibility tool, you can also rerun your SYCL code after it has come out of the tool on your Nvidia hardware and check that everything works correctly and that performance is what you expect. After you have done that, you can just work on the SYCL variant and maintain one single source for all your platforms. If you are writing your SYCL or oneAPI applications, they will now work on CUDA unmodified. If you want to force using the CUDA backend, you can always use a custom CUDA selector. Stuart will show some examples later. The SYCL code is compiled in the same way. If you use DPC++ extensions for performance, your mileage might vary. Not all of them are supported at the moment, but support for those relevant for Nvidia hardware will come in the near future. CUDA-specific extensions may also appear in the future as well, to enable specific features or better support integration with existing code bases. However, all of these are optional features, and developers can enable and disable them depending on the hardware they are targeting. That's how we keep a single source that is compatible and efficiently running on different platforms. Using the interop task feature, we can also call now existing libraries from the CUDA ecosystem, such as CUBLAS or CUFFT. This allows SYCL and oneAPI applications to leverage native performance for key parts of the codebase. It also expands what you can normally do with CUDA libraries. Now they are easily integrated with the SYCL data dependency mechanism. The SYCL runtime can figure out the dependencies and schedule all data transfers efficiently for the libraries to execute. The nodes on the SYCL DAG can span multiple devices and contexts, so programming complex heterogeneous hardware becomes much simpler. You can now, for example, easily combine an FPGA kernel with a call to CUBLAS on an Nvidia GPU in the same source, just by having two different queues to two different devices.
So now we're going to talk about using SYCL for CUDA, and the first thing that needs to be discussed is the project's requirements. So Linux is the required OS for SYCL for CUDA, with Ubuntu 18.04 being the preferred distro. This is the platform that we build and test on, so it's easily the most stable and supported distro for a SYCL for CUDA application. The project's runtime makes use of APIs introduced in CUDA 10.1, so it will not run on anything older than that. And the hardware that you use with SYCL for CUDA needs to support SM50 or above. So how do you get your hands on SYCL for CUDA? Well, the project is open source and it's been merged into the upstream Intel LLVM repo. This repo contains guides and instructions on how to enable support for Nvidia GPUs. While the repo contains binary distributions of the compiler, these binaries do not have CUDA support, so those seeking support for Nvidia GPUs need to compile the project from source. Instructions on how to compile the project with support for CUDA are included in the project's Getting Started guide, which is linked to in the README. So how do we use SYCL for CUDA? There actually isn't that much to it outside of a couple extra compiler flags and environment variables. No changes are necessary to your project's SYCL source code. If you want to compile a simple test application, you only need to worry about these two flags, SYCL and SYCL targets. The first of which tells the compiler that your project is a SYCL application. The second of which tells the compiler that its kernel should be compiled down to a specific format. Because we are targeting CUDA, we want to compile to PTX, which is why we set this triple. Before we can run our application, we need to tell the SYCL runtime that we want it to dynamically load the CUDA backend, which is why we set the SYCL backend environment variable to PI CUDA. If you're interested in seeing SYCL for CUDA in action, we've written some sample applications on a public GitHub repo. These projects demonstrate how to write device selectors that will actually pick up a CUDA device. They also demonstrate interop with a native CUDA API. Each sample contains a CUDA application and a SYCL application so that the two approaches can be easily compared. This is a repo that we are actively working on, so if you're interested in seeing what SYCL for CUDA can do, check it out. So now we're going to discuss the design of SYCL for CUDA. SYCL for CUDA was born out of a number of discussions within Khronos, where we started to evaluate the SYCL 1.2.1 programming model as a good C++ programming model for heterogeneous architectures. We started to wonder what we could do to extend the SYCL specification so that it could target more than just OpenCL platforms. This, of course, was not the original intention of the SYCL group, which started as a subgroup of OpenCL, but it's been gaining interest for a while because of the flexibility that C++ provides in integrating with existing libraries. The first target that was suggested to the SYCL working group was Vulkan, and there's still a lot of interest in that. However, it's a large task, and there are already existing paths that will enable this, such as the CLVK project. The target that everyone compares SYCL with is CUDA. CUDA, of course, is very popular in the data center and HPC domains. It has a large customer base, it has a lot of traction from a large community, and it has a large ecosystem, a wealth of existing libraries and tools. A few years ago, we started to add experimental support for PTX generation in Compute CPP using the Nvidia OpenCL platform. However, we had mixed results. There were concerns about features and performance, and the version of OpenCL that ships with the CUDA toolkit is 1.2. So SYCL for CUDA, in a way, is our continuation of that discussion. It will help us to identify how we can generalize the SYCL specification in order to enable it to run on different backends. So when we started looking into running SYCL on top of CUDA, we started to identify a number of features that work and a number of features that don't. Our initial thoughts were Nvidia provide an implementation of OpenCL 1.2 on top of CUDA, so our job should be relatively simple for the SYCL features that map closely to OpenCL 1.2. In reality, there are a number of things that do work and a number of things that don't. One of the things that works really well is the OpenCL platform model. If you think about it, we have devices, context, platforms. These are all things with clear equivalents inside the CUDA driver API, which makes it a relatively easy feature to implement. Some other things, we have the memory and execution models for OpenCL 1.2. Those could be used as is. We have some additional performance-enabled features such as subgroups. Those can be implemented, but we found that they were outside of the scope of our initial work. Some other things, though, will not work at all. One of the big things is OpenCL Interop. In SYCL 1.2.1, this is a really important feature, but it simply cannot work with CUDA at all. It's not always easy to get the CUDA equivalent object because it's not always a one-to-one mapping. And also the return types of those interop functions is a OpenCL type, which means that we can't overload them with a CUDA type. As previously discussed, one of the big motivators for this project is actually interop and integrating with existing libraries. So we needed interop for this project to be successful. Later on in this discussion, we will look at how we achieve this by implementing a number of extensions. Another large part of the SYCL spec is image support. Images in CUDA work very differently than that of OpenCL. One of the main differences is that images in CUDA are sampled on construction, whereas in OpenCL they are sampled within the kernel. There is no path via the CUDA driver API to emulate this OpenCL behavior. A large chunk of the initial work has been done to create a new image and sampler class that can be mapped to CUDA, but that is still being discussed internally within Khronos. The compilation model of OpenCL is also different from CUDA. Let's have a look at some of the implementation details of SYCL for CUDA. This diagram represents how a SYCL application interacts with the DPC++ runtime. At the top, we've got our application, containing numerous device binaries. This links to the DPC++ runtime library, which implements the SYCL API and the execution memory models. This library does not call any OpenCL or CUDA functions directly. Instead, we've got this layer of indirection here. So this layer of indirection is a new API called the Plugin API, or PI API. This is a C API that is based on OpenCL. Instead of calling a native API directly, the SYCL runtime will call PI API, which will then call down to the native API. This effectively decouples the SYCL runtime from any specific backend. If anyone wants to introduce a new backend, they just need to implement the PI API interface and create a new shared library. Each backend is implemented as a shared library. Multiple backends can be loaded at once, which will allow the programmer to take advantage of multiple backends within one application. Here's a simple look at the PI API design. At the top, we've got a PI API function, PyMemBufferCreate. At the bottom left is the OpenCL implementation of that function. Because OpenCL maps so closely to the design of PI API, this function is actually just a simple wrapper around CL create buffer. If we look at the bottom right instead, we have the CUDA implementation, which is significantly more complicated, and I actually needed to crop it to fit it onto this slide. This is because CUDA does not map as well to an OpenCL-like API design, so the PI CUDA implementations of each function tend to be a little bit more complicated than the OpenCL equivalent. PI CUDA works really well, but there's a number of limitations inside the current implementation. As it currently stands, a context can only have a single device, there is no image support, and there is no online compilation. Image support is something that we touched upon earlier as a particular pain point in adapting CUDA to the SYCL programming model. The same problem is here, there's just no way to map CUDA's image API to that of OpenCL. To configure PI API, there's a number of environment variables that can be used. Earlier we saw that you have to specify the SYCL backend environment variable to tell the application to use the CUDA backend. This is true, and what is actually going on is that you're telling the SYCL runtime to load the PI CUDA library. In addition to this, we have the SYCL PI trace environment variable, which configures how the SYCL runtime will log every single PI API call. If we look at the right-hand side of the screen, we'll see what that looks like. We have every single PI API call made by the SYCL runtime. It prints the name of the function called, its arguments, and the return value. This is a feature that's been quite popular with our contributors. And it's quite helpful because it means that you can get a quick idea of what's going on inside the runtime without having to fire up a debugger. Let's have a look at some of the new interop features that we have introduced to SYCL for CUDA. So interop is a massive feature in SYCL 1.2.1. Many of the SYCL objects actually encapsulate an internal OpenCL object, and you can access that through the getMember function. Obviously, we're not using OpenCL anymore, so a lot of these features do not work for CUDA. So we had to come up with a solution that lets us achieve interop with a CUDA backend. This brings us to the SYCL generalization proposal. This is a proposal that seeks to decouple SYCL from OpenCL. It introduces a number of new APIs and features that make this a lot easier. You can query the backend of a SYCL object at runtime. You can access the internal object through a new getNative function, which takes a enum class specifying the backend. And you can create SYCL objects through native objects through a make function. getNative is one of the features that we've borrowed from this proposal and implemented in SYCL for CUDA. It's quite simple, it's a free function. It takes in a SYCL object and returns its underlying native object. To achieve this, there is a new enum class called backend, and it contains enumerators for OpenCL, CUDA, and host backends. You specify this when you call getNative as a template parameter, and through some template wizardry, it will figure out the correct return type for that call. So if you pass it a SYCL context and you specify the CUDA backend, it will return a Q context. If you specify the CUDA backend and you pass it a SYCL queue, it will return a Q stream. And this works for the SYCL context, SYCL queue, SYCL device, and SYCL event objects. Not all of the features of the generalization proposal are implemented in SYCL for CUDA. The getNative function, of course, that's the one we needed the most and we spent the most time on, but there isn't an implementation of the make function. So you cannot create a SYCL object from a CUDA object inside SYCL for CUDA. So now that we have getNative, we can access the internal CUDA object of a SYCL object, and that's great. That's a really big step in the right direction, but it's not enough. For us to be able to tap into that existing ecosystem of CUDA libraries and tools, we need to be able to call a CUDA API and to schedule that work alongside all the rest of our SYCL functionality. And right now that's simply not possible. There's nothing that will help us achieve that in SYCL 1.2.1. So what we need is some new extensions. So to achieve this, we're going to borrow from another existing proposal. This is the Codeplay Interop task proposal, and that is essentially the exact functionality that I described before. It is a new set of functionality that's added to the command group handler that lets you call into a third-party API and to schedule it alongside all of the rest of your SYCL code. It uses the exact same dependency tracking mechanisms as a normal SYCL kernel. So this means that you can call into a native third-party API and have all of that stuff scheduled for you. Here's an example of it being used. You can see here that we are accessing the queue from the interop handler, and we specify the backend as CUDA so that the queue we access is actually the queue stream. Here we are accessing the CUDA memory objects, and of course we cast this to a float pointer, so that's just an array of floats, and this will let us get the memory that we're going to pass into the CUDA API function, which we do here. And it's as simple as that. The dependencies are tracked because we're still using accessors. It's still essentially idiomatic SYCL code, and it all just works. Let's have a look at the OneMKL project and how we use SYCL for CUDA's interop features to enable it to work on Nvidia hardware. OneMKL is a math kernel library. Developers can use it to target Intel CPUs, GPUs, and now Nvidia GPUs as well. In order to achieve the best performance possible on Nvidia hardware, the OneMKL library uses a cuBLAS backend, cuBLAS of course being the CUDA-based hardware accelerated implementation of BLAS. In order to achieve the best performance, OneMKL does not abstract the cuBLAS backend behind any kind of interfaces or anything like that. It calls those routines directly. It accesses CUDA memory and context directly from the SYCL objects. It creates a one-to-one association between a SYCL context and the underlying CUDA context and a cuBLAS library handle. The DPC++ runtime manages any sort of dependencies between different calls to cuBLAS routines using the same dependency tracking mechanisms that it uses for SYCL kernels. If you'd like to see any of the interop features that we've discussed being used in a real-world application, I would suggest having a look at the cuBLAS backend to OneMKL. In here you can see a lot of interesting code, including uses of the getNative function and interop task. Here is an example of getNative being used. You can see here that we are accessing the underlying CUDA representation of two SYCL objects, the device and context. This is a little bit of machinery to make sure that the correct context is set before we call any of the cuBLAS routines. And if we go to the next slide, we can actually see that. So here we're using the interop task to call into a cuBLAS function. And of course, this will get scheduled alongside all of the other SYCL code. Many of you will be curious about the performance results of SYCL for CUDA, and we're very pleased with them so far. Here's an example of some benchmarks we've been running. This is Babel Stream. Babel Stream is a benchmark that measures memory transfer rates to and from global memory on GPUs. Here we're comparing SYCL for CUDA with a normal raw CUDA approach to OpenCL for CUDA. And as you can see, the results for SYCL for CUDA are actually very, very close to that of CUDA. These benchmarks were ran on CUDA 10.1 on a GeForce GTX 980. And if you're curious about the BabelStream benchmark, we've included the link here.
Okay, let's summarize our thoughts and see what is coming afterwards in our work. In this webinar, we have shown how you can use DPC++, Intel's open source SYCL compiler, to run your SYCL applications on Nvidia hardware, and how you can interact with native CUDA code and libraries. You can try today by building from source the DPC++ LVM project with CUDA support, following the instructions that are on the website. Currently, we are focusing on having a complete implementation for SYCL 1.2.1 features, so that we can ensure the SYCL specification can be implemented completely on the CUDA backend. So far, most of the difficult parts are done, and the only main feature we are missing is image support, which we are coming with different plans on how we can do it. We are also working on different performance enhancements. There is a lot of opportunities for improvements, since so far we have been focusing on being feature complete. So if you want to collaborate or simply report some problem, join us in the Intel LVM GitHub repo, mark issues related to CUDA with the CUDA label so we can see it. Sometimes it takes a while for us to reply, but we see them all. Feel free to look into the pull request and even to contribute to some features. And that was all. Thanks everyone for attending this webinar, and hopefully see you around contributing to the SYCL community and playing around with Nvidia CUDA backend.